Deep beneath the rural fields and sleepy alpine villages that straddle the border between France and Switzerland lies an engineering marvel that stretches 17 miles around in a continuous subterranean loop. Approximately 100 feet under the surface, a machine of unprecedented scale accelerates subatomic particles to velocities fractionally shy of the speed of light. Late in the year 2025, this colossal apparatus spat out a measurement that sent quiet shockwaves through the global physics community, threatening to shatter a theoretical framework that researchers have relied upon and tested relentlessly for half a century. This is the story of CERN, the Large Hadron Collider, and a subtle, stubborn anomaly known as the penguin decay, a mysterious signal that refuses to go away and hints at entire chapters of reality that remain completely unwritten. To grasp the sheer magnitude of what happens beneath the European countryside, one must first visualize the architecture of the machine itself. The Large Hadron Collider is housed inside a circular tunnel so vast that it crosses an international boundary line, looping effortlessly out of Swiss territory into France and back again. Walking a full lap on foot would consume the better part of a day, which is why the scientists, engineers, and technicians who maintain the facility routinely ride bicycles through the subterranean corridors just to travel from one sector to another. At its core, the machine is designed to do one primary thing with terrifying precision. It takes streams of protons, the tiny positively charged building blocks found inside the nucleus of an atom, and accelerates them in opposite directions around the 17-mile ring. These protons are not merely moving quickly, they are hurled around the loop at roughly 670 million miles an hour, completing more than 11,000 revolutions every single second. Keeping particles locked into a circular trajectory at relativistic speeds requires an immense application of force. To achieve this, the tunnel is lined with thousands of superconducting electromagnets that are chilled to temperatures colder than the empty void of interstellar space. Engineers cool these massive magnets down near absolute zero using liquid helium, ensuring they can carry staggering electrical currents without generating resistance or melting under the strain. Once the magnetic fields are locked in place, the machine steers two opposing beams of protons into a direct, head-on collision. The resulting impact is so violently energetic that for a microscopic fraction of a second, the temperature at the collision point spikes to levels over 100,000 times hotter than the center of our sun. In that fleeting flash, the collider recreates a tiny echo of the primordial universe, mirroring the conditions that existed less than a single second after the Big Bang. Out of the wreckage of these high-energy smashes, a chaotic spray of exotic particles bursts outward, most of them vanishing into nothingness almost instantly. Capturing the traces of these ephemeral entities is the entire justification for building a 17-mile machine and freezing its magnets colder than deep space. Every single collision leaves behind a trail of microscopic clues, breadcrumbs pointing toward the fundamental rules that govern existence, and recently those clues have begun whispering something deeply unsettling. To understand why this whisper has rattled researchers, one must first look at the ruling paradigm of modern physics, a remarkably successful framework known simply as the Standard Model. Imagine a periodic table designed not for chemical elements, but for the fundamental constituents of reality itself. The Standard Model catalogs every basic particle discovered thus far, including the quarks that bind together to form protons, the nimble electrons that buzz around atomic nuclei, and a handful of heavy exotic cousins that flicker briefly in and out of existence. For 50 years, this single theoretical list has passed every rigorous test thrown at it by experimentalists. Whenever the mathematical equations predicted the existence of a new particle, scientists eventually built the necessary machinery, ran the experiments, and found the particle sitting precisely where the theory promised it would be. It correctly anticipated the existence of the W and Z bosons, successfully called the top quark, and finally triumphed in 2012 with the discovery of the Higgs boson, a particle hunted for nearly half a century. Yet, despite this legendary track record of predictive success, physicists have known for decades that the Standard Model is fundamentally incomplete. It completely fails to account for gravity, offers no explanation for the invisible dark matter that dominates the mass of the cosmos, and remains utterly silent on why matter exists in the universe at all, instead of canceling out entirely with antimatter in the beginning. Researchers have long suspected that hidden pages are missing from this master rulebook, and the Large Hadron Collider was constructed explicitly to push the theory until it finally cracked under the strain. For years, the machine pushed forward, and the standard model stubbornly held its ground, returning results that were almost annoyingly accurate. That was until a mountain of accumulated data began to reveal a glaring discrepancy. Observing what happens during a particle collision requires cameras of unimaginable scale and sophistication. CERN wraps its primary collision points in detectors the size of multi-story buildings. The largest of these, known as Atlas, towers over a 6-story structure and matches the weight of the Eiffel Tower, while another massive detector named CMS outweighs 30 fully loaded jumbo jets combined. These detectors do not take traditional photographs of individual particles, which are far too small to be seen directly. Instead, they function like detectives following footprints in fresh snow, tracking the trails left behind as particles punch through successive layers of sensitive material. Because the entire detector sits within a powerful magnetic field, moving particles have their trajectories bent. Heavy particles curve only slightly, while lighter ones bend sharply, allowing computers to identify what kind of particle flew past, even if its lifespan was shorter than a trillionth of a second. The sheer volume of data generated by these collisions is staggering, with detectors facing roughly 40 million snapshots every single second. To prevent the world's hard drives from overflowing instantly, lightning-fast trigger computers make split-second decisions, discarding the mundane majority of crashes and preserving only the rarest and most interesting events. While giant detectors like Atlas and CMS search for brand-new, never-before-seen particles, a specialized detector called LHCb adopts a different strategy. Rather than hunting for heavy monsters directly, LHCb studies how certain unstable particles fall apart over time, searching for microscopic deviations between theoretical predictions and empirical reality. In physics, the process of a heavy, restless particle breaking down into lighter, calmer pieces is known as decay. Many particles carry excess energy and cannot remain stable, shattering almost as soon as they are born in a manner akin to a delicate snowflake melting upon warm skin. The standard model dictates strict probabilities for how these decays should occur, outlining exact percentages for common breakups versus rare ones. By measuring these decay patterns over billions of collisions, scientists can use them as a unique fingerprint to test whether nature is truly obeying its own mathematical laws. Most decays conform perfectly to expectations, but the rarest breakups serve as the ultimate traps for discovering hidden physics. If an unknown, exceptionally heavy particle exists just out of reach of direct creation, its invisible presence can still exert a subtle pull on a rare decay, nudging the process slightly off course. This brings us to a specific, highly coveted decay process that physicists affectionately and bizarrely refer to as the penguin. The story behind the name dates back to the 1970s, when a young researcher lost a casual wager over a game of darts and was required to insert the word penguin into an upcoming academic paper. While drawing the complex diagram representing a particular rare particle breakup, complete with its characteristic loops and dangling lines, he remarked that the sketch bore a vague resemblance to a penguin standing upright. The moniker stuck as an inside joke, and today serious scientists at CERN discuss penguin decays with entirely straight faces, recognizing them as one of the most sensitive probes available in modern science. The star of this specific mystery is a particle known as the B meson, a heavy little blob born during proton collisions that contains a weighty building block called the beauty quark. Because of its internal composition, the B meson is inherently unstable and decays almost immediately. While the vast majority of B mesons break apart in ordinary, predictable ways, roughly once in every million tries, a rare penguin decay occurs, causing the meson to shatter into 4 smaller particles simultaneously. This rare collection includes lightweight fragments like kaons and pions, alongside a pair of muons, which are essentially heavier, more powerful cousins of the electron. The LHCb collaboration spent years combing through an astronomical data set encompassing roughly 650 billion recorded B meson crashes. They isolated the tiny sprinkle of rare penguin events and analyzed not merely how often the decay happened, but the precise geometric angles at which the resulting muons and other particles flew away from the wreck. The standard model provides a rigorous prediction for this angular distribution, offering a clean score designed to strip away difficult mathematical uncertainties and provide a fair test of the rules. When the collaboration compared their empirical measurements against the theoretical demands of the standard model, the numbers stubbornly refused to align. The discrepancy first appeared in 2013, when researchers noticed a slight angular drift away from the predicted values. At the time, the signal was faint, easily dismissed as a potential statistical fluke that might vanish once more data was accumulated. However, when a larger data set was analyzed in 2016, the wobble persisted, pointing in the exact same direction and maintaining a similar magnitude. By December of 2025, the LHCb team rolled out their most comprehensive and thoroughly cleaned analysis to date, drawing upon years of accumulated wreckage and hundreds of billions of evaluated decays. Instead of washing away, the anomaly grew stronger when researchers calculated the statistical significance of the gap between the measurement and the theoretical prediction. It crossed a threshold known as 4 sigma. In the language of particle physics, sigma measures how confident researchers can be that a result is not simply the product of random chance or everyday statistical noise. A 1 sigma result is common and uninteresting, comparable to missing the center of a dartboard by an inch. 2 sigma signals prompt a second look, while 3 sigma results begin to raise eyebrows. 4 sigma, however, represents a profound departure from ordinary luck. At the 4 sigma level, the probability that random statistical fluctuation could produce a discrepancy this large drops to approximately 1 in 16,000. To put that into perspective, imagine standing in a massive stadium packed with 16,000 people, where only a single individual holds a winning ticket, and successfully blindfolding yourself and grabbing that exact ticket holder on the first try. That is how unlikely it is for the penguin wobble to be an accidental quirk of chance. When the collaboration announced these updated findings, the immediate reaction among physicists was a mixture of intense excitement and deep caution. Despite the striking odds, particle physics maintains arguably the harshest and most disciplined evidentiary standards in all of science. A 1 in 16,000 chance is impressive, but it does not constitute an official discovery. In the rigorous world of high-energy physics, researchers demand a 5 sigma standard before they are permitted to claim a formal discovery. At 5 sigma, the odds of a statistical fluke plummet to less than 1 in a million, approaching roughly 1 chance in 2 million. This uncompromising threshold exists for a very good reason, rooted in a historical trap known as looking everywhere. Because CERN operates multiple detectors simultaneously and generates countless measurements across thousands of potential decay channels over many years, rare statistical anomalies are bound to pop up purely by accident somewhere in the massive sea of data. Much like a massive national lottery where individual odds of winning are microscopic, selling enough tickets ensures that someone will eventually win by pure coincidence. Past physics experiments have been burned repeatedly by exciting signals that looked rock solid initially, only to evaporate into thin air as soon as fresh data arrived. Consequently, 5 sigma serves as an unyielding wall protecting the scientific method from premature celebration, ensuring that anomalies must earn their place through overwhelming, inescapable proof. Therefore, even with a stubborn 4 sigma wobble that has survived for over a decade, the standard model technically remains standing, bruised and trembling, but not yet dethroned. Yet the most compelling aspect of the 2025 analysis was not just that the LHCb detector saw the anomaly grow, but that a completely independent machine operating at the exact same facility observed the very same ghost. The CMS detector, a heavyweight apparatus managed by a separate competing army of scientists with entirely different hardware, software, and analytical methodologies, turned its gaze toward the same penguin decay. When the CMS collaboration processed their independent data, They found that their measurements also drifted away from the standard model prediction in the exact same direction and by a comparable amount. While the CMS measurements lacked the razor-sharp precision of the LHCb dataset, the agreement between two independent, fiercely competing teams using entirely different machinery transformed the conversation overnight. In observational science, a lone anomaly detected by a single instrument can easily be blamed on a localized instrumental glitch or a subtle software bug. But when two independent observers looking through different windows report seeing the exact same shadow, dismissing the phenomenon becomes nearly impossible. Even with this powerful cross-confirmation from two separate giant detectors, the final verdict remains suspended in a tense limbo. The 5 sigma wall stands unbroken, keeping the official status of the anomaly filed firmly under the category of a tantalizing, highly persistent maybe. Yet the implications are profound. For 50 years, the standard model has reigned supreme as the ultimate blueprint of reality, shrugging off every challenge hurled against it. Now, as researchers continue to refine their data and peer deeper into the subatomic wreckage produced beneath the border of France and Switzerland, the most successful rulebook in scientific history faces its most severe trial yet, leaving the physics community waiting anxiously to see if the missing pages of the universe are finally about to be revealed. While the independent confirmation from both the LHC-B and CMS collaborations provided a massive adrenaline boost to the global physics community, seasoned veterans of the particle physics world know better than to pop the champagne prematurely. The history of high-energy exploration is littered with the ghosts of anomalies past, fleeting whispers of new phenomena that ultimately dissolved into the mundane background noise of statistical fluctuations or calibration oversights. To fully appreciate why the scientific establishment maintains such a fierce, almost monastic restraint in the face of these compelling numbers, one must examine the intricate web of alternative explanations that theorists and experimentalists alike must meticulously rule out before rewriting the textbooks. The most persistent ghost haunting any precision measurement at the Large Hadron Collider is not an undiscovered supersymmetric particle or an exotic fifth force of nature, but rather the stubborn, insidious nature of background noise. When protons slam into one another at relativistic speeds, they do not produce a clean, orderly stream of isolated events. They unleash a chaotic, blinding tempest of debris. Millions of particles spray outward in every fraction of a second, creating a dense forest of tracks, electromagnetic showers, and secondary interactions that the massive detectors must disentangle in real time. Even with sophisticated trigger algorithms operating at lightning speed to filter the wreckage, the sheer volume of collisions means that ordinary, well-understood standard model processes can occasionally mimic the rare signatures of interest. A mundane decay process, occurring billions of times more frequently than the elusive penguin, can sometimes shed a particle or mismeasure an angle in just the right way to masquerade as a rare event. If the computer algorithms tasked with reconstructing these particle paths harbor even a minuscule hidden bias, a tiny flaw in how magnetic bending is calculated, or how energy deposition is calibrated across thousands of individual sensor channels, that systematic error will be faithfully reproduced across millions of events, creating a persistent phantom signal that looks for all the world like a genuine deviation from theory. This is precisely why the rivalry between experimental groups like LHCb and CMS is so vital, yet also why it demands such rigorous cross-examination. While it is true that having two independent detectors observe the same angular drift significantly strengthens the argument that the effect is not merely an instrumental glitch unique to a single machine, it does not automatically eliminate the possibility of a shared theoretical blind spot. Both detectors rely upon complex, highly sophisticated Monte Carlo simulations to model what the standard model predicts their instruments should see. These massive software suites are written by human beings, and despite being subjected to peer review and relentless validation tests, they are masterpieces of approximation. If an underlying assumption built into the foundational simulation software is subtly flawed, both detectors could be systematically misinterpreting their data in the exact same direction. Recognizing this vulnerability, A dedicated faction of theorists and data analysts spent the months following the December 25 data release engaged in a grueling exercise of forensic auditing. They tore into the software pipelines, re-examined the alignment of silicon tracking layers down to the micron level, and tested alternative models of how background contamination might bleed into the signal region. Every potential source of systematic error, from subtle variations in beam luminosity to the complex quantum interactions of particles passing through detector shielding, was subjected to intense scrutiny. The goal was not necessarily to debunk the anomaly, but to survive the intellectual gauntlet of skepticism. In science, a claim is only as robust as the objections it has successfully withstood, and the penguin wobble was forced to stand trial against every conceivable non-new physics explanation the community could dream up. As the months ticked by and the audit reports were finalized, the results brought a surprising degree of comfort to the experimentalists. The anomaly stubbornly refused to go away. The systematic uncertainties, while carefully documented and quantified, were not large enough to explain away the growing gap between measurement and prediction. The 4 sigma significance held firm, protected by layers of rigorous cross-checks that left both proponents and skeptics with a lingering, inescapable sense of unease. Something genuine was happening in the data. The mathematical discrepancy was real, repeatable, and robust against methodological changes. Yet, confirming that a measurement is genuinely anomalous is only half the battle. The far more daunting challenge lies in explaining what physical reality could possibly be causing it. If the standard model is indeed failing at this specific junction, what is taking its place? What kind of hidden machinery could reach into a rare B meson decay and subtly alter the angular distribution of its decay products without violating any of the countless other precision tests the theory has successfully passed over the last 5 decades? To answer this question, theoretical physicists have had to venture far beyond the comfortable boundaries of established knowledge, exploring speculative realms that sound more like science fiction than empirical science. For years, the favorite escape hatch for theorists struggling with the limitations of the standard model has been a concept known as supersymmetry. Often abbreviated as SUSY, this elegant hypothesis proposes that every known particle in the universe possesses a heavier, undiscovered superpartner waiting in the wings. In the symmetric utopia of the early universe, these partners walked hand in hand with their lighter counterparts. But as the cosmos cooled and the fundamental forces broke apart, the supersymmetry shattered, leaving the superpartners heavy, unstable, and largely hidden from view. According to SUSY advocates, the Large Hadron Collider was always destined to be the machine that flushed these elusive partners out of hiding. The heavy squarks, sleptons, and gauginos imagined by the theory would provide the perfect virtual intermediaries to nudge rare penguin decays off course. Because these superpartners would be too massive for the collider to create directly in head-on collisions, they would remain invisible, detectable only through their ghostly fingerprints left behind on delicate decay angles. For a long time, supersymmetry was treated not just as a leading hypothesis, but almost as an article of faith among theoretical physicists, an exquisite mathematical symmetry that simply had to be true to rescue the elegance of the universe. However, as the Large Hadron Collider completed run after run without ever catching a single direct glimpse of a superpartner, enthusiasm for the simplest versions of supersymmetry began to wane. The energy thresholds climbed higher, the exclusion plots filled in with discouraging shades of gray, and the theory was forced to undergo increasingly complex adjustments to keep pace with the negative results pouring out of the detectors. If supersymmetry is indeed the answer to the penguin anomaly, it is not the clean, minimalist framework theorists originally envisioned, but a messy, highly constrained variant that requires fine-tuning to survive contact with reality. This frustration has driven researchers to explore even more radical alternatives, pushing the boundaries of theoretical imagination. Some physicists have turned their attention to the possibility of entirely new fundamental forces mediated by undiscovered vector bosons, sometimes colloquially referred to as dark photons or Z-prime particles. Unlike the familiar forces of electromagnetism or the strong nuclear interaction, These hypothetical forces might interact exclusively with specific families of particles, perhaps playing favorites with the heavy leptons known as muons while leaving electrons largely untouched. Such a flavor non-universal force would act like a clandestine bridge between the visible sector of the universe and a shadowy, hidden sector of particles we cannot yet see, subtly tilting the scales of decay pathways and generating precisely the kind of angular anomalies observed by LHCb and CMS. Other theorists have resurrected ideas involving composite models of matter, suggesting that quarks and leptons are not truly fundamental points at all, but rather bound states constructed from even smaller, more primordial constituents held together by a hyperpowerful force yet to be described. In such a framework, the B meson is not merely a simple blob of beauty and up quarks, but a complex microuniverse whose internal dynamics can be perturbed by composite substructures, leading to unexpected deviations when stretched to its breaking point under the extreme conditions of a proton-proton collision. The sheer diversity of these theoretical proposals highlights both the excitement and the anxiety gripping the physics community. An anomaly without a clear theoretical explanation is a frustrating puzzle. A locked door standing at the end of a long hallway with no obvious key in sight. Theorists have flooded the academic literature with hundreds of speculative papers, each attempting to construct a bespoke mathematical framework that can account for the 4 sigma wobble while simultaneously respecting every other piece of experimental data gathered across decades of particle physics research. Yet finding a single, cohesive model that fits all the constraints without creating contradictions elsewhere has proven to be an excruciatingly difficult puzzle. While the theoretical debate rages on, the ultimate arbiter of this scientific drama remains the machine itself. The Large Hadron Collider does not care about elegant mathematics, theoretical prestige, or the philosophical comfort of textbooks. It operates solely on the cold, uncompromising mechanics of nature. And crucially, the machine is not done running. Following extensive upgrades designed to increase luminosity and sharpen collision tracking, the collider has embarked on subsequent operational phases aimed at accumulating even massive troves of collision data. The strategy moving forward is as simple as it is daunting. Collect more data, push the statistical significance higher, and force the universe to reveal its hand once and for all. If the penguin wobble is merely a remarkably persistent statistical ghost, accumulating billions upon billions of additional B meson decays will eventually dilute the anomaly, washing the signal away into the smooth, predictable curves of the standard model as the error bars shrink and the truth asserts itself. But if the anomaly is real, if those stubborn angular scores continue to sit off to the side as the dataset swells, the statistical significance will inexorably climb. 4 sigma will inch closer and closer to that magical, untouchable threshold of 5 sigma. Reaching 5 sigma in the coming years would transform the conversation instantly. The cautious whispers in conference hallways would give way to open celebration, and the 50-year reign of the standard model would officially enter its twilight era. It would mark the dawn of a new physics, opening up uncharted territory that researchers have spent decades dreaming about. The discovery of a confirmed crack in our most fundamental understanding of reality would instantly reorient global scientific priorities, driving the design of even larger, more powerful colliders capable of probing the new energy scales where these hidden forces and particles presumably reside. Conversely, if the signal fades away into the statistical noise, the disappointment will be palpable, but the scientific enterprise will march forward unfazed. That is the paradoxical beauty of the process that plays out deep beneath the Swiss and French countryside. Every experiment, whether it confirms our deepest expectations or shatters our most cherished assumptions, drives humanity one step closer to an accurate understanding of the cosmos. Whether the penguin decay ultimately proves to be the key that unlocks a hidden universe or merely another phantom haunting the history of science, the journey itself remains one of the most astonishing intellectual adventures in human history. As technicians recalibrate the superconducting magnets, as beams of protons resume their blinding race around the 17-mile loop, and as detectors prepare to capture millions of fresh snapshots of creation's earliest moments, the world holds its collective breath. The machine is humming once again in the dark, spinning up to speed, ready to test the very limits of what we know, and perhaps to finally turn the page on a universe we are only just beginning to comprehend. The relentless pursuit of answers deep beneath the European countryside touches upon something profoundly fundamental about the human condition, echoing an ancient drive to peer past the horizon and question the fundamental nature of the ground beneath our feet. For generations, humanity has looked up at the vast expanse of the night sky or inward toward the microscopic architecture of matter, driven by an unquenchable curiosity to understand the hidden gears turning behind the scenes of reality. Every scientific revolution, from the Newtonian mechanics that map the graceful dance of planets to the bizarre, counterintuitive rules of quantum mechanics and relativity, has been born from moments precisely like this. Moments where well-established certainties began to buckle under the weight of stubborn, unyielding anomalies. Consider the historical parallels that shadow the current state of particle physics. At the close of the 19th century, classical physics reigned supreme, an intellectual monolith so comprehensive and successful that many leading scientists believed nearly everything worth discovering had already been found. The universe was viewed as a vast, predictable clockwork mechanism governed by the immutable laws of motion and electromagnetism. Yet, lingering on the periphery were a few tiny, seemingly insignificant anomalies, such as the bizarre behavior of black body radiation and the curious constancy of the speed of light regardless of motion. Those minor cracks in the classical edifice did not quietly go away. Instead, they served as the dynamite that blew open the doors to the 20th century, ushering in the revolutionary paradigms of quantum mechanics and Einsteinian relativity. Today, the Standard Model occupies a remarkably similar throne, standing as an astonishingly successful intellectual achievement that has guided our understanding of the subatomic realm for half a century. Yet, just like the classical physicists of yesteryear, modern researchers are acutely aware that their master framework is incomplete, sitting atop yawning chasms of ignorance regarding gravity, dark matter, and the fundamental asymmetry of matter and antimatter in the cosmos. The penguin anomaly, with its stubborn 4 sigma wobble persisting across multiple independent detectors and years of grueling data collection, carries the unmistakable scent of those historical cracks. It whispers of a deeper layer of reality, a hidden landscape of particles and forces operating just beyond the current limits of our technology. To appreciate the sheer scale of the intellectual leap required if this anomaly is confirmed, one must consider what it truly means to rewrite the foundational laws of physics. It is not merely a matter of adding a new entry to a list or tweaking a mathematical constant. It requires a fundamental conceptual expansion of our worldview. If new forces or particles are ultimately discovered to explain the B meson decay discrepancies, they will fundamentally alter how we understand the evolution of the universe, from the searing heat of the Big Bang to the complex, structured cosmos we inhabit today. These hidden elements could hold the key to solving the cosmological puzzles that have baffled astronomers and astrophysicists for decades, bridging the frustrating disconnect between the microscopic domain of quantum particles and the macroscopic realm governed by gravity. Moreover, the technological fallout from pushing the boundaries of particle physics often extends far beyond the confines of academic laboratories, rippling out to transform everyday human life in ways that initial investors could never have anticipated. The pursuit of extreme energy collisions and ultra-precise detectors has historically driven monumental leaps in engineering, materials science, and computational power. The most famous example, of course, is the World Wide Web, which was originally invented at CERN by Tim Berners-Lee to help international teams of physicists share complex data seamlessly across disparate locations. Technologies developed to build superconducting magnets, process petabytes of collision data in real time, and construct hypersensitive radiation detectors frequently find transformative applications in medical imaging, cancer treatment therapy, cybersecurity, and global telecommunications. When society invests billions of dollars and years of human ingenuity into building a 17-mile machine beneath the border of France and Switzerland, the return on investment cannot be measured solely in the narrow ledger of academic papers published or particles discovered. It is measured in the expansion of human capability, the rigorous sharpening of our collective problem-solving faculties, and the cultivation of a scientific culture that refuses to accept comfortable dogma when nature itself is offering contradictory clues. The physicists hunched over computer screens late into the night, meticulously auditing background noise, debating alternative theoretical models, and wrestling with statistical significance thresholds, are participating in a grand, multi-generational enterprise that defines the very best of what civilization can achieve. As the Large Hadron Collider continues its high-intensity runs, churning out billions of fresh proton collisions every second, the tension within the global scientific community remains palpable. Every new dataset analyzed brings researchers one step closer to resolving the mystery once and for all. Will the anomaly dissolve into the statistical background noise, taking its place alongside historical phantoms that ultimately vanished under the glare of more rigorous data? Or will it stubbornly hold its ground, climbing past the elusive 5 sigma threshold to become the gateway discovery of a brand new era in fundamental physics? The answers will not arrive overnight, nor will they come without fierce debate, relentless cross-examination, and countless hours of painstaking analysis. But that is precisely the beauty of the scientific method in action. It is a slow, rigorous, self-correcting crucible designed to ensure that when we finally declare we have discovered something new about the universe, we can stand behind that claim with unshakable confidence. Until that definitive verdict is reached, the penguin wobble remains a tantalizing beacon, a microscopic crack in the master rulebook of reality that beckons daring minds to look closer, dig deeper, and prepare themselves for whatever astonishing truths may be waiting just beneath the surface of the visible world. The journey to the edge of human knowledge is rarely a straight path paved with immediate triumphs. Far more often, it is a winding labyrinth of false starts, agonizingly slow progress, and moments of profound doubt that test the resilience of those who dare to venture into the unknown. When we contemplate the monumental scale of the Large Hadron Collider, stretching its 17-mile loop beneath the picturesque pastoral landscapes of France and Switzerland, it is easy to view it merely as a triumph of brute engineering, a colossal subterranean ring of steel, superconducting wire, and high-tech sensors capable of recreating the hellish temperatures of the infant universe. Yet, the true power of CERN lies not in its physical dimensions or the raw energy of its proton beams, but in the collective intellect, skepticism, and relentless curiosity of the thousands of human beings who dedicate their lives to interpreting the cryptic language of its data. Every single second that the machine operates, it generates an ocean of information so vast and overwhelming that human minds alone could never hope to process it. Millions of collisions erupt simultaneously, sending showers of subatomic shrapnel crashing through the multi-layered chambers of detectors like ATLAS, CMS, and LHCb. In this chaotic storm of energy and matter, fascinating phenomena are constantly born and snuffed out in fractions of a trillionth of a second. The ability to filter this digital deluge, to separate the mundane background noise of well-understood physical processes from the faint, trembling whispers of potential new physics, represents an extraordinary triumph of modern data science and collaborative organization. It requires international teams of physicists, computer scientists, and engineers to work in synchronized harmony, pooling their expertise to build sophisticated algorithms and analytical pipelines capable of holding complex statistical models up to the harsh light of empirical reality. Yet, as the ongoing saga of the penguin anomaly demonstrates, possessing the most powerful instruments ever created does not grant immediate immunity to the humbling uncertainties of scientific exploration. The 4 sigma wobble that has persisted for over a decade in the decay patterns of B mesons serves as a constant, sobering reminder that nature does not give up her deepest secrets easily. Every time researchers believe they have cornered a new phenomenon, they are immediately confronted by the rigorous demands of their own discipline, forced to submit their findings to a brutal gauntlet of skepticism, peer review, and independent replication. The insistence on the 5 sigma threshold for a formal discovery is not an arbitrary bureaucratic hurdle designed to frustrate ambitious researchers. It is an essential cultural immune system developed over centuries of trial and error, protecting the scientific community from the alluring trap of self-deception and the seductive comfort of finding what it desperately wants to see, rather than what is actually there. This cultural commitment to rigorous self-doubt is precisely what makes science such a uniquely powerful tool for understanding the universe. In many other walks of life, like strongly held beliefs are defended with emotional fervor and insulated from contradictory evidence. In fundamental physics, by contrast, the highest honor a researcher can achieve is often proving that an old, cherished paradigm is fundamentally flawed. Thereby opening the door to a deeper and more comprehensive understanding of reality. If the Standard Model, this magnificent 50-year-old intellectual monument that has weathered every experimental challenge thrown at it, finally cracks beneath the pressure of independent confirmations from competing detectors like LHCb and CMS, the physicists who spent their entire careers testing it will not mourn its passing with despair. Instead, they will celebrate it as the ultimate victory of empirical inquiry over theoretical dogma, eagerly rolling up their sleeves to dive into the uncharted conceptual territory that lies beyond the fracture. The implications of such a breakthrough extend far beyond the specialized subdisciplines of particle physics, rippling outward to touch upon foundational questions that have captivated human imagination for millennia. What is the true nature of mass? A force of the invisible architecture that binds the cosmos together, from the smallest quantum fluctuations to the grandest sweeping galaxies. How did a universe born out of a searingly hot, featureless fog of quark-gluon plasma manage to cool, structure itself, and eventually give rise to conscious observers capable of looking back at the stars and asking how they came to be? These are not merely academic inquiries. They are expressions of a deep-seated human desire to find our place in the grand narrative of existence, to decode the ancient instructions written into the fabric of space and time. As the Large Hadron Collider continues its relentless cycles of operation, backed by continuous technological upgrades, sharper timing resolution, and expanding datasets, the global scientific community stands poised on the razor's edge of potential history. Whether the stubborn angular anomalies in rare B meson decays ultimately cross the threshold into undeniable discovery or slowly fade into the background noise of statistical fluctuation, the process itself remains an awe-inspiring testament to human ingenuity. It proves that despite our inherent limitations, despite the staggering complexity of the cosmos and the frustrating elusiveness of its deepest truths, we possess the courage to build machines that reach toward the dawn of time, the discipline to hold our hopes in check against the cold demands of evidence, and the enduring wonder required to keep searching for the missing pages of the universe. When we trace the lineage of scientific thought from the philosophical musings of ancient atomists who first dared to imagine an indivisible limit to matter, all the way to the colossal superconducting ring of the Large Hadron Collider buried beneath the pastoral tranquility of the French and Swiss border, we are witnessing a continuous, unbroken thread of human ambition. We are a species compelled to look past the superficial appearance of things, refusing to accept the chaotic surface of reality as the final word. Instead, we build, we test, we measure, and we break things apart on purpose, all in the desperate, beautiful hope of catching a fleeting glimpse of the invisible gears that turn behind the curtain of existence. Consider the sheer audacity required to construct a machine like CERN. To take a tunnel 17 miles in circumference, plunge it 100 feet beneath farms, villages, and the jagged roots of the Alps, and line it with thousands of electromagnets chilled to temperatures colder than the empty voids of deep space is already an engineering feat that borders on the mythological. But the true marvel is not simply that the machine works, or that it can accelerate streams of protons to more than 670 million miles an hour, forcing them into catastrophic head-on collisions 11,000 times every single second. The true marvel is what happens in the aftermath of those collisions, the deliberate, meticulous, and agonizingly careful reconstruction of an infant universe. In that microsecond flash of extreme heat, when temperatures spike to levels 100,000 times hotter than the center of our sun, the Large Hadron Collider achieves something that no other place in the known cosmos can replicate on demand. It rolls back the clock of reality, melting protons down into a primordial soup of unchained quarks and flowing gluons, the very same quark-gluon plasma that filled the universe in the first frantic microseconds after the Big Bang. By studying how this smoothest of all liquids flows and cools, scientists are literally reading the lost first chapter of creation, searching for the hidden mechanisms that somehow steered a featureless, searing fog into the complex, star-studded cosmos we call home today. Yet, as we have explored throughout this deep dive into the strange signals caught at CERN, every answer extracted from the wreckage of a high-energy collision only serves to expose deeper, more confounding questions. For 50 years, the Standard Model of particle physics has stood as the undisputed heavyweight champion of scientific theories. It is a master rulebook, a periodic table for the truly tiny, compact, and elegant mathematical framework that has successfully predicted the existence of particles decades before experimentalists ever laid eyes on them. From the W and Z bosons to the top quark and the legendary Higgs boson, the Standard Model has shrugged off every challenge thrown at its feet, cementing its status as the most rigorously tested and accurate idea in the history of human thought. And yet, every physicist worth their salt knows a dark secret that keeps them awake in the quiet hours of the night. The rulebook is undeniably incomplete. It is a magnificent map that covers vast territories of the subatomic world, but it leaves massive, gaping blank spaces labeled with terrifying admissions of ignorance. It has nothing to say about gravity, the ubiquitous force that keeps your feet planted firmly on the floor. It offers zero explanations for the invisible dark matter that outweighs all visible stars and galaxies combined, acting as the gravitational glue holding the cosmos together. Most hauntingly of all, it fails to explain why matter exists in the universe at all. Why the cataclysmic birth of the cosmos did not result in an absolute, symmetrical annihilation where matter and antimatter canceled each other out completely, leaving behind nothing but an ocean of lonely photons. Because theorists and experimentalists alike know that pages are missing from this master text, the Large Hadron Collider was built with a singular, provocative purpose: to push the Standard Model until it finally cracked. For years, the machine pushed and the model held firm, returning results that were almost annoyingly perfectly aligned with theoretical predictions. The scientific community began to whisper among themselves, wondering if their most powerful machine would merely confirm what they already knew, never finding a single true crack in the foundation. Then came the data from the LHC-B detector, whispering of a rare and delicate process known to insiders by its delightfully absurd nickname, the penguin decay. This is not a messy, chaotic collision where particles shatter in plain sight. It is a pristine, incredibly rare breakup of a B meson containing a beauty quark, occurring roughly once in every million tries. Because the process is so impossibly delicate, it acts like a perfectly still alpine lake. If an unknown, massive particle is lurking just out of reach in the dark, too heavy for the collider to ever create directly, its invisible hand will still reach into that tranquil pond and send ripples across the surface. And ripples were indeed found. When researchers analyzed the angular distribution of the particles flying away from these rare penguin decays, The numbers refuse to match the strict demands of the standard model. What started as a faint, dismissible whisper back in 2013 stubbornly refused to wash away with fresh data. Over the years, as the LHCb collaboration gathered more collisions and cleaned their datasets with increasing rigor, the anomaly did not fade, it grew stronger. By late 2025, the statistical significance of the discrepancy reached 4 sigma. In the language of particle physics, 4 sigma is a profound and unsettling milestone. It means that the probability of this wobble being an accidental fluke of random statistical noise is roughly 1 in 16,000. It is the equivalent of walking into a massive stadium packed to the brim with 16,000 cheering fans, blindfolding yourself, reaching into the crowd, and instantly grabbing the single person holding the golden ticket. For any other field of science, odds like that would be more than enough to pop the champagne, rewrite the textbooks, and declare an unmitigated triumph. Yet particle physics is notoriously ruthless. It operates under a self-imposed discipline that is crueler and more uncompromising than almost any other human endeavor. 1 in 16,000 is not a discovery. It is officially filed under a tantalizing, agonizing maybe. Why? Because of the look everywhere trap, the sobering historical reality that when a machine is checking tens of thousands of different channels and measuring countless decay pathways year after year, a 4 sigma blip is bound to pop up somewhere purely by accident, like a lucky ticket holder winning a massive national lottery. History has burned physicists too many times with ghost signals that looked rock solid at first glance, only to evaporate into thin air the moment additional data poured in. To prevent themselves from being fooled by their own enthusiasm, the global physics community enforces an unyielding wall of proof known as the 5 sigma standard. At 5 sigma, the odds of a statistical fluke plummet to less than 1 in a million, approaching roughly 1 chance in 2 million. Only when a signal climbs past that towering barrier are scientists permitted to stand before the world and pronounce the word discovery without fear of professional embarrassment. Until that threshold is crossed, the standard model technically remains standing, bruised and trembling under the weight of a decade-long anomaly, but not yet dethroned. Yet, what transformed the penguin wobble from an interesting statistical curiosity into one of the most compelling mysteries in modern science was the intervention of a rival machine. Across the 17-mile ring from LHCb sits CMS, a monolithic detector weighing more than 30 fully loaded jumbo jets, operated by a completely separate army of researchers with entirely different hardware, software, and analytical methodologies. When the CMS team trained their instruments on the exact same rare B meson decays, they did not find a contradiction. They found the same anomaly pointing in the same direction by a comparable amount. In the high-stakes arena of experimental science, a lone anomaly observed by a single detector can always be dismissed as an instrumental quirk, a localized calibration error, or a subtle software bug unique to that machine. But when 2 independent detectors, built by competing teams using entirely different technologies, stare through different windows at the same subatomic wreckage and report seeing the exact same shadow, the conversation changes overnight. Dismissing the phenomenon becomes an exercise in willful ignorance. While the 5 sigma wall still stands untouched, keeping the official status locked in suspense, the psychological reality within the physics community has shifted irrevocably. If this stubborn wobble continues to swell as the Large Hadron Collider embarks on its subsequent phases of high-intensity data collection, and if it finally breaches that sacred 5 sigma barrier, the implications will ripple across the entire intellectual landscape of humanity. It will mark the official end of the Standard Model's unchallenged reign, signaling the dawn of an entirely new era in fundamental physics. Theorists will be forced to dust off their most radical blueprints, whether exploring supersymmetric superpartners, exotic dark photons, or composite substructures of matter, and test them against a reality that has officially proven itself stranger and more expansive than our equations ever dared suggest. Conversely, if future datasets ultimately dilute the signal, washing the anomaly away into the smooth, predictable curves of established theory, The disappointment will be palpable across global laboratories. But even in defeat, the scientific enterprise loses nothing of value. The relentless pursuit of truth through rigorous self-doubt, independent replication, and unyielding skepticism is itself the ultimate victory. It proves that we are willing to build magnificent machines, hold our most cherished hopes up against the cold, hard light of empirical evidence, and submit our deepest assumptions to the uncompromising judgment of nature. As the superconducting magnets hum softly in the subterranean dark, chilling their coils down to temperatures that mock the void between the stars, and as streams of protons resume their blinding race around the 17-mile loop, the universe waits quietly. We are standing at the edge of a vast, uncharted intellectual ocean, staring across a tiny, stubborn ripple in the data that just might be the first sign of an undiscovered continent. Whether it proves to be a phantom of statistics or the gateway to a revolutionary new understanding of reality, the journey down into the machinery of creation remains the greatest adventure our species has ever undertaken. The continuous quest to understand the deepest operating principles of the universe has recently entered one of its most intellectually electric phases, driven by ongoing discoveries and intense analytical debates centered around CERN's sprawling subterranean complex. While the broader scientific community watches with bated breath, researchers working directly with the data streams flowing out of detectors like LHCb and CMS are grappling with fresh nuances that complicate the narrative of a simple, clean break in our foundational laws. In recent months, as specialized seminars have rolled out updated datasets regarding flavor-changing neutral currents and delicate left flavor universality tests, the plot has thickened in ways that showcase the true, messy, self-correcting nature of cutting-edge research. To appreciate the bleeding edge of what is unfolding inside these international research collaborations, one must look beyond the simple binary of whether a theory is proven right or wrong, and examine the subtle war of calculations happening in theoretical offices across the globe. While the 4 sigma anomaly observed in the angular distributions of rare penguin decays has stubbornly held its ground, recent theoretical reexaminations have thrown a fascinating wrench into the machinery of interpretation. Some prominent theoretical physicists have pointed out that calculating the exact contributions of standard model charm quark loops, the complex quantum fluctuations that occur dynamically within the core of these meson breakups, carries inherent calculation hurdles. Depending on the specific theoretical approach utilized to model these intricate quantum chromodynamic backgrounds, the statistical tension of the anomaly can experience shifts, leaving a fraction of the community debating whether the wobble reflects brand new fundamental forces or a previously unappreciated subtlety in how we compute strong interaction physics. This ongoing scientific dialogue does not diminish the gravity of the work. Rather, it elevates it. It highlights why particle physics is uniquely resilient against premature declarations of victory. At the same time that teams are auditing penguin decay pathways, related tests focusing on lepton flavor universality, such as probing the precise branching fraction ratios of heavier meson states involving tau leptons versus muons, have continued to show persistent lingering tensions with standard theoretical expectations. These parallel lines of investigation reinforce the central theme that the standard model, for all its historic triumphs, is surrounded by an encroaching perimeter of unexplained anomalies. Even when individual measurements undergo intense scrutiny and recalibration, the overall landscape remains one of profound anticipation, where every single percentage point of refined data brings researchers closer to an absolute resolution. The technological roadmap supporting these investigations is equally awe-inspiring, looking far ahead toward the future capabilities of the facility. Plans are already well underway for high-luminosity upgrades designed to radically multiply the sheer volume of proton-proton collisions harvested by the detectors. By scaling up integrated luminosity by orders of magnitude over the coming years, experiments will shift from operating with statistical samples that yield 4 sigma hints to accumulating datasets large enough to definitively settle whether these elusive signals cross the sacred threshold of 5 sigma or gracefully dissolve into the smooth curves of established theory. This impending data deluge ensures that the subterranean corridors beneath the Swiss and French countryside will remain the global epicenter of fundamental discovery for decades to come. Ultimately, the enduring magic of this scientific endeavor lies in its absolute transparency and institutional humility. Every seminar, every peer-reviewed critique, every recalculation of background noise, and every rival cross-check between independent detector teams represents humanity at its most intellectually rigorous. Whether the eventual outcome requires introducing entirely new families of hypothetical gauge bosons like Z-prime particles, invoking exotic leptoquarks that bridge the gap between quarks and leptons, or simply forcing us to rewrite our textbooks regarding quantum chromodynamics, the journey itself is a magnificent triumph. It is a living demonstration that our species is eternally unwilling to settle for an incomplete map of reality, choosing instead to build 17-mile rings of superconducting wonder and peer directly into the fiery dawn of time itself. The horizon of modern particle physics extends far beyond the immediate boundaries of the current Large Hadron Collider ring, pointing toward an ambitious future of technological scale and conceptual daring that will define scientific exploration for the remainder of the 21st century. Even as researchers meticulously analyze the subtle angular deviations of rare B meson decays and debate the statistical nuances of 4 sigma anomalies, the engineering teams and accelerator physicists at CERN are already deep into the next monumental phase of evolution for the complex. This upcoming chapter centers around the High Luminosity Large Hadron Collider, a massive upgrade program designed to radically transform the machine's capabilities and unleash an unprecedented deluge of collision data into the digital pipelines of global detectors. To appreciate what the high luminosity upgrade represents, one must understand the fundamental bottleneck that currently limits high-energy experimentation. Finding ultra-rare events like the penguin decay is not merely a matter of accelerating protons to near-light speeds. It is a brutal numbers game governed by probability. Because these specific breakups occur only once in roughly 1 million interactions, researchers require vast oceans of recorded collision data to fish out enough clean examples to achieve statistical significance. The more collisions a machine can produce and record per second, the faster those sparse needles can be found within the cosmic haystack. The high luminosity upgrade achieves this by fundamentally rethinking how proton beams are focused, manipulated, and steered into each other at the heart of the massive detectors. Engineers are installing advanced components such as compact, high-field superconducting quadrupole magnets crafted from exotic niobium tin alloys, capable of squeezing the colliding proton beams down to microscopic widths far tighter than anything previously accomplished. When these denser, more tightly focused bunches of protons cross paths inside detectors like ATLAS and CMS, the number of simultaneous interactions per crossing skyrockets, dramatically multiplying the total integrated luminosity delivered to the experiments over their operational lifetimes. Yet, achieving this torrential flow of data introduces an extraordinary engineering paradox that pushes human ingenuity to its absolute limits. Increasing the number of overlapping collisions per crossing creates a punishing phenomenon known to accelerator physicists as pileup. When dozens of proton pairs smash into each other simultaneously in the exact same microspot, their resulting particle debris showers overlap inside the detector chambers, creating a blinding chaotic fog of electronic noise. Untangling that overlapping chaos requires detectors to possess not only extreme spatial resolution, but also astonishing temporal precision. The ability to timestamp individual particle tracks with a resolution measured in picoseconds, determining not just where a particle flew, but the exact fraction of a nanosecond it was born. To meet this challenge, research and development teams have spent years designing entirely new generations of silicon pixel detectors, ultra-fast timing layers, and radiation-hardened electronics capable of surviving the blistering radiation environment near the core collision points without degrading. These technological breakthroughs do not merely serve the narrow interests of fundamental physics. They frequently cascade outward into society, transforming fields as diverse as medical diagnostics, where ultra-precise particle tracking and radiation detection translate directly into vastly improved positron emission tomography scanners and targeted hadron therapy treatments for cancer patients. Looking even further ahead, the scientific community is already casting conceptual blueprints for the ultimate successor to the current 17-mile ring, a proposed megamachine known as the Future Circular Collider. Envisioned as a colossal subterranean loop stretching approximately 60 miles in circumference, this hypothetical next-generation collider would dwarf the existing infrastructure, pushing collision energies into uncharted territories that could finally reveal the true mass scales of supersymmetric partners, heavy vector-vector bosons, or exotic leptoquarks. Designing a machine of that magnitude requires international cooperation on an unprecedented scale, uniting governments, academic institutions, and industrial partners across continents to solve logistical, financial, and environmental challenges that would have seemed impossible just a generation ago. This spirit of global collaboration is perhaps the most remarkable aspect of the entire CERN enterprise, that standing as a shining counterpoint to a geopolitical landscape so often fractured by division and conflict. Inside the vast control rooms, office complexes, and underground assembly caverns, thousands of scientists, engineers, technicians, and students work side by side, transcending national borders, cultural backgrounds, and political tensions. When academic papers detailing breakthrough measurements are published, their author lists routinely span dozens of pages, cataloging hundreds of contributors from scores of different nations. In this unique subculture, nationality and ideology dissolve into a shared universal language of mathematics, empirical skepticism, and relentless curiosity. The sociology of these massive scientific collaborations operates on a fascinating, highly disciplined set of internal rules designed to prevent bias and maintain absolute intellectual integrity. Before any major dataset is made public or submitted to rigorous peer review, it must pass through internal review committees, consisting of critical colleagues whose explicit job is to tear the analysis apart, hunt for hidden systematic errors, and challenge every assumption made by the primary data analysts. This rigorous internal peer review process ensures that by the time a result like the penguin anomaly is presented to the wider world, it has already survived the harshest possible interrogation from the very people who understand the equipment and the mathematics best. It is within this uncompromising intellectual crucible that the ongoing drama of the Standard Model's potential fracture unfolds day after day. The persistence of the 4 sigma anomaly over more than a decade is not an accident of poor oversight or rushed conclusions. It is the enduring result of careful, multi-layered validation executed by brilliant minds who are acutely aware of the historical traps that caught their predecessors off guard. Whether future datasets ultimately push this stubborn wobble across the sacred 5 sigma finish line to crown a new era of physics, or gently resolve the tension into the smooth, predictable curves of established theory, the process itself remains a magnificent monument to human rationality. We are living through a golden age of foundational exploration, an era where 17-mile machines freeze magnets colder than deep space, collide fundamental pieces of matter at fractions of the speed of light, and recreate the searing primordial fog of the universe's birth on demand. The questions driving this grand enterprise are as old as human consciousness itself, touching upon why we are here, what holds our reality together, and what hidden chapters remain unwritten in the master text of existence. As the beams begin another lap, circling endlessly beneath the quiet hills of the Alps, the world holds its collective breath, waiting to see if the universe is finally ready to reveal its deepest secrets. The sheer scope and intellectual depth of what takes place within the sprawling subterranean architecture of CERN cannot be overstated, as every single layer of its operation represents a monumental triumph of human coordination, engineering mastery, and uncompromising scientific discipline. When we dive deeper into the daily reality of the thousands of researchers who inhabit this subterranean world, we uncover a culture defined by an extraordinary blend of intense skepticism and unyielding passion for discovery. The physicists, software engineers, cryogenic specialists, and hardware technicians who maintain the Large Hadron Collider are not merely operators of a colossal machine. They are guardians of an empirical threshold, standing watch at the absolute frontiers of human comprehension. To truly grasp why the ongoing saga of the penguin decay and its persistent 4 sigma anomaly holds such immense psychological and intellectual weight for this community, one must immerse themselves in the rigorous day-to-day grind of data analysis that happens far away from the public eye. When a major collaboration like LHCb or CMS prepares to release a new set of findings, the process involves months of grueling, meticulous work behind closed doors. Teams of analysts divide into independent subgroups, each taking a different algorithmic approach to reconstruct particle trajectories, estimate background contamination, and model the complex quantum chromodynamic interactions that govern the behavior of heavy quarks within decaying B mesons. These subgroups work in isolation from one another, intentionally blind to each other's intermediate results, to ensure that personal biases, shared expectations, or unconscious desires to see a specific outcome cannot bleed into the methodology. Once these independent analyses reach their conclusions, the groups reconvene for what is often described as a tense, high-stakes internal reconciliation process. Every discrepancy between the models is exhaustively debated, every potential source of systematic uncertainty is placed under a microscope, and every line of code is audited for hidden flaws. If one subgroup's methodology yields a slightly different angular distribution score than another, the discrepancy is not simply swept under the rug or averaged away. It is aggressively investigated until its root cause is fully understood and accounted for. This ruthless internal vetting procedure is the secret lifeblood of modern particle physics. It ensures that by the time a statistical anomaly like the penguin wobble is declared robust enough to be presented at an international conference or submitted to a peer-reviewed journal, it has already survived the harshest possible cross-examination from the scientists who understand the detectors and the underlying mathematics better than anyone else on Earth. This extraordinary level of institutional self-discipline and sheds light on why veteran researchers react with such measured, cautious restraint when outsiders or media outlets become overly eager to declare the death of the standard model. In a world accustomed to instant gratification and rapid-fire news cycles, the glacial, highly methodical pace of particle physics can feel agonizingly slow. Yet, that deliberate slowness is precisely what protects the scientific enterprise from the embarrassing pitfalls of premature declaration. The ghosts of past anomalies, signals that flared brightly with statistical promise in early data sets, only to evaporate into the background noise as soon as more data arrived, serve as a permanent, humbling reminder of how easily human perception can be tricked by random statistical fluctuations and subtle instrumental quirks. This historical awareness is why the 5 sigma threshold remains an unyielding, sacred wall within the community. It is an agreed-upon cultural compact that distinguishes between a tantalizing hint and an absolute historical breakthrough. When an anomaly sits at 4 sigma, as the penguin wobble currently does, it commands intense respect and rigorous follow-up, but it is fundamentally treated as an unresolved mystery rather than a confirmed discovery. It occupies a fascinating purgatory in the landscape of science, loud enough to keep theorists awake at night drafting hundreds of speculative mathematical models, yet quiet enough to prevent experimentalists from tearing up the textbooks just yet. The theoretical fallout that accompanies this lingering ambiguity is a spectacle in its own right, showcasing the boundless creativity of the human mind when confronted with a genuine conceptual puzzle. Theoretical physics departments across the globe have transformed into buzzing hubs of intense debate, with researchers attempting to construct comprehensive frameworks that can neatly accommodate the angular anomalies observed in Bs and decays, without breaking any of the countless other precision tests the standard model has successfully passed over the last 5 decades. Some theorists lean heavily into the elegant mathematics of supersymmetry, exploring complex, constrained parameter spaces where undiscovered superpartners act as invisible intermediaries, nudging decay angles off course. Others venture down more exotic avenues, proposing the existence of brand new fundamental gauge bosons, flavor non-universal forces, or composite substructures of matter that challenge our most basic assumptions about what constitutes an elementary particle. Yet, amidst this flurry of theoretical speculation, the ultimate arbiter remains the cold, uncompromising machinery housed deep beneath the European countryside. The Large Hadron Collider continues its relentless cyclic operation, accelerating proton beams to velocities fractionally shy of the speed of light, guiding them into catastrophic head-on collisions and flooding global computing grids with fresh oceans of raw data. Every upgrade to the superconducting magnets, every refinement to the silicon tracking layers, and every advancement in real-time trigger algorithms brings the international collaborations closer to resolving the tension once and for all. As the high luminosity upgrade program prepares to push integrated luminosity to unprecedented heights, the statistical sample sizes will swell exponentially, ensuring that the 4 sigma whisper will either be decisively silenced by the overwhelming weight of new data or triumphantly amplified past the 5 sigma finish line into the history books. Whatever the ultimate verdict turns out to be, the journey itself remains an awe-inspiring testament to the enduring power of human curiosity and cooperative ambition. It proves that despite our inherent biological limitations, despite the staggering complexity of the subatomic realm and the frustrating elusiveness of nature's deepest secrets, our species possesses the collective will to build 17-mile machines, freeze magnets colder than deep space, and stare unflinchingly into the fiery dawn of time. As the beams complete yet another invisible lap beneath the quiet hills of the Alps, the global scientific community waits in breathless anticipation, ready to embrace whatever astonishing reality the universe is finally prepared to unveil. The philosophical weight of this ongoing scientific pursuit extends far beyond the technical jargon of cross-sections, invariant masses, and angular distribution coefficients, touching upon the oldest human aspirations to understand our place in the cosmos. When we contemplate the sheer scale of the apparatus buried beneath the rolling hills of the French and Swiss frontier, we are looking at a mirror reflecting our own collective intellectual evolution. Every major breakthrough in the history of science has been preceded by a period of profound uncertainty, a confusing twilight zone where old certainties no longer suffice and new paradigms have yet to be fully born. The persistent anomalies and stubborn data discrepancies currently keeping researchers awake in their subterranean control rooms are the direct modern descendants of those historical moments of transition, serving as the friction that sparks true paradigm shifts. To fully appreciate the gravity of what hangs in the balance, one must reflect on the fragility of human knowledge and the humbling realization that everything we currently understand about the subatomic world might be just a specialized, low-energy approximation of a much grander, more intricate reality. For half a century, the Standard Model has reigned supreme as the ultimate intellectual monument of reductionist science, successfully cataloging the fundamental building blocks of nature and explaining how they interact through 3 of the 4 known fundamental forces. Yet, its very successes have only served to cast its glaring omissions into sharper relief. The absence of gravity, the silence regarding dark matter, and the total inability to account for the matter-antimatter asymmetry of the universe are not minor aesthetic blemishes. They are massive architectural voids at the base of our theoretical temple. When an experiment like the Large Hadron Collider sets out to test this framework to its absolute breaking point, it is doing something profoundly courageous. It is deliberately constructing high-energy crucibles designed to challenge our best ideas, inviting nature to prove us wrong if our equations are incomplete. The 4 sigma wobble observed in rare penguin decays represents the tangible fruit of that courage, a persistent, repeatable, and thoroughly audited signal that suggests the universe is playing by rules we have not yet fully decoded. Whether this specific anomaly ultimately turns out to be the long sought doorway into an undiscovered landscape of supersymmetric partners, flavor non universal fuzz, or exotic leptoquarks, or whether it ultimately dissolves under the weight of even higher statistics datasets, the mere fact that we have built a machine capable of asking the question is an extraordinary triumph. The human element of this grand enterprise is equally compelling, highlighting a rare and precious aspect of civilization that transcends geopolitical friction and cultural division. Inside the global collaborations operating the massive detectors, thousands of individuals from dozens of nations work together in seamless coordination, bound by a shared universal language of empirical skepticism and mathematical rigor. There are no political boundaries, ideological filters, or national rivalries when it comes to analyzing the tracks left by a decaying beamison or debating the calibration parameters of a silicon tracking layer. In an era where human societies are so frequently fractured by conflict, isolationism, and dogmatic certainty, the collaborative culture of CERN stands as a shining beacon of what can be achieved when humanity unites around a common, noble purpose: the pursuit of objective truth about the universe we share. As we look toward the horizon of future upgrades, higher luminosities, and conceptual designs for even larger circular colliders, the momentum of discovery shows no sign of slowing down. The technical hurdles are immense, demanding continuous innovations in cryogenics, data processing, machine learning algorithms, and precision manufacturing. Yet, the engineers, technicians, and theorists driving these initiatives do not view these challenges as obstacles to be avoided, but as invitations to excel. They understand that every advancement made in the service of fundamental physics eventually cascades outward into broader society, enriching medical diagnostics, improving computing architectures, and expanding the boundaries of human technological capability. The journey down into the machinery of creation is, at its core, a journey inward into the nature of consciousness itself. We are star stuff, examining the stars, organized collections of quarks and leptons capable of building 17-mile machines to smash themselves apart on purpose, all to ask how we came to be and what invisible rules govern our existence. As the beams of protons continue their relentless, invisible laps through the dark tunnels beneath the Alps, circling endlessly while the world above goes about its daily life, the stage is set for the next great chapter of human discovery. Whatever answers lie waiting in the unwritten pages of the future, the quest itself remains the greatest, most breathtaking adventure our species has ever undertaken. The quiet hum of the cryogenic plants keeping the superconducting rings at temperatures colder than interstellar space serves as a constant rhythmic heartbeat for a community dedicated to pushing back the boundaries of the known. Above ground, ordinary life moves forward across the farms and alpine villages of the French-Swiss border, completely unaware that miles beneath their feet, humanity is actively interrogating the fundamental fabric of existence. Every single proton beam injection, every meticulously timed crossing inside the collision halls, and every terabyte of data funneled into the sprawling computing grids represents another small step into the great unknown. When we reflect on the sheer scale of ambition required to sustain such an enterprise over decades, it becomes clear that the value of CERN extends far beyond any single measurement, anomaly, or theoretical paper. It is an enduring monument to human capability, proving that our species possesses the unique capacity to organize globally, build impossibly complex machines, and submit our most cherished ideas to the harshest possible empirical scrutiny. The stubborn 4 sigma wobble of the penguin decay may eventually resolve into a revolutionary new physics or fade gracefully into the background noise of established theory. But the pursuit itself has already forever altered how we perceive our place in the cosmos. The integration of advanced artificial intelligence and machine learning architectures directly into the core trigger systems of CERN represents a silent revolution that has fundamentally transformed how data is filtered and processed in real time. In the past, the brutal computational bottleneck required blunt algorithmic choices to discard millions of collision snapshots instantly, risking the permanent loss of rare, unconventional signatures that did not fit neat, pre-programmed search criteria. Today, highly specialized machine learning models deployed on field programmable gate arrays operate at the absolute speed of light within the detector electronics themselves. These neural networks possess the unprecedented ability to recognize complex, multidimensional patterns of particle tracks on the fly, identifying subtle anomalies, displaced vertices, and unexpected energy deposits microseconds after a collision occurs. This technological leap has effectively widened the digital keyhole through which rare events must pass, ensuring that potential hints of new physics are preserved with a fidelity that previous generations of hardware could never achieve. Beyond the computational revolution, the infrastructure surrounding the Large Hadron Collider has undergone remarkable ecological and technological adaptations that rarely make mainstream headlines, but are vital for the facility's ongoing survival. Operating a machine of this magnitude demands staggering amounts of electrical power, requiring sophisticated energy management strategies that align with modern environmental standards. In recent years, CERN has pioneered innovative heat recovery systems that capture the thermal energy generated by the massive cryogenic refrigeration plants and redirect it to heat municipal buildings and residential districts in nearby local communities. This closed-loop approach to energy conservation demonstrates how cutting-edge fundamental research can actively integrate with regional sustainability efforts, turning the waste heat of subatomic discovery into a practical utility for everyday citizens. At the same time, the detector collaborations are increasingly turning to quantum-inspired algorithms and exploring the integration of quantum sensors to tackle the escalating complexity of high-luminosity data environments. As the machine prepares for higher collision rates, the sheer density of overlapping tracks threatens to overwhelm even the most sophisticated classical silicon tracking layers. Quantum sensing technologies, which leverage superposition and entanglement to achieve hyper-precise spatial and temporal measurements, offer a tantalizing glimpse into the future of particle detection. By deploying sensors capable of recording particle trajectories with sub-picosecond timing resolution, researchers hope to cleanly separate simultaneous collisions that occur in the exact same microspot, effectively neutralizing the blinding fog of pile-up noise that threatens to obscure tomorrow's most delicate discoveries. These technological advancements are mirrored by an equally dramatic evolution in the global theoretical landscape, where researchers are increasingly looking beyond traditional perturbative calculations to tackle the stubborn anomalies in flavor physics. Theoretical departments are deploying advanced numerical lattice gauge theory, massive computations executed on some of the world's most powerful supercomputers, to model the behavior of quarks and gluons from first principles with unprecedented accuracy. These lattice calculations are crucial because they help untangle whether subtle quantum chromodynamic effects have been undercalculated in standard model predictions, providing a rigorous mathematical mirror against which experimental anomalies like the B-meson decay discrepancies can be tested without relying on historical approximations. The international scope of this intellectual endeavor continues to expand, drawing in talent, funding, and collaborative partnerships from nations across every continent. Initiatives like the worldwide LHC computing grid have evolved into sprawling, decentralized digital ecosystems that link academic institutions, national laboratories, and commercial cloud providers into a unified network capable of crunching exabytes of collision data. This distributed computing model has become a blueprint for global scientific cooperation, proving that solving humanity's most complex technical challenges requires an open, borderless architecture where data flows freely and collaborative peer review is valued above national prestige. Looking toward the horizon, the conceptual planning for the Future Circular Collider has moved from abstract whiteboard discussions into concrete geological, environmental, and financial feasibility studies. Like drilling test cores deep into the rock strata beneath the Geneva Basin, engineers and geologists are meticulously mapping the subterranean fault lines and soil compositions required to house a 60-mile ring. Such a machine would push center-of-mass collision energies into the multi-TeV range, opening up entirely uncharted energy landscapes where the true mass scales of dark matter mediators, heavy neutrinos, and extended Higgs sectors could finally be probed directly, rather than inferred through delicate decay angles and indirect ripples. Yet, even as blueprints are drawn for machines that will not see first beam until the middle of the century, the immediate focus remains locked onto the ongoing runs of the current facility. Every day that the superconducting magnets stay cold, every hour that the proton beams maintain their focus, and every cycle of data analysis conducted by the competing detector teams brings humanity closer to resolving the tensions that have kept the physics community on edge. Whether the answers ultimately confirm our deepest theoretical suspicions or shatter our models beyond recognition, the machinery in the dark continues its relentless rotation, waiting patiently for the universe to yield its next great secret. The rhythm of discovery at the world's premier particle physics laboratory is punctuated not just by the sudden flash of high-energy collisions, but by the grand, deliberate transitions of its operational life cycle. Following the dramatic conclusion of the Large Hadron Collider's third major data-taking period, the subterranean complex beneath the French and Swiss border recently entered a monumental phase of transformation known as Long Shutdown 3. As the final proton beams of Run 3 were safely dumped from the 17-mile ring, the multi-year metamorphosis officially began, marking a pivotal turning point for every major experimental collaboration stationed along the underground loop. This planned hiatus is far from a period of quiet dormancy. Rather, it represents one of the most intense and complex engineering campaigns in CERN's illustrious history. Thousands of engineers, technicians, cryogenic specialists, and researchers have flooded the subterranean tunnels to dismantle, upgrade, and completely reinvent core systems in preparation for the high-luminosity LHC era. Over a kilometer of the machine's inner infrastructure is currently being systematically replaced, including the installation of revolutionary new superconducting quadrupole magnets forged from advanced alloys, and the integration of precision crab cavities designed to tilt colliding proton beams to maximize interaction rates. These upgrades will radically multiply the collider's overall intensity, setting the stage for an unprecedented surge of data when the machine fires back up toward the end of the decade. Even as the massive accelerator pauses its proton-smashing duties to undergo this structural overhaul, the scientific harvested from years of accumulated data continues to yield stunning breakthroughs. Just weeks before the transition into long shutdown, the LHCb collaboration announced a landmark discovery that triumphantly closed a chapter of theoretical physics stretching back more than 60 years. By sifting through massive repositories of collision data, researchers identified and confirmed the final missing member of the doubly charmed baryon family, an elusive composite particle consisting of two heavy charm quarks paired with a strange quark. Because the mass disparities between these constituent quarks introduce extreme internal dynamics, mapping this newly captured particle provides theorists with an invaluable laboratory for testing how quantum chromodynamics operates under the most demanding conditions imaginable. This milestone accomplishment underscores the quiet, relentless persistence that characterizes daily life within specialized detector groups like LHCb. While general-purpose giants like Atlas and CMS command headlines with searches for supersymmetric partners and high-mass exotic resonances, forward-facing detectors focus intensely on the intricate nuances of heavy flavor physics, matter-antimatter asymmetries, and rare decay channels. Every successful identification of a rare particle state, every precise measurement of an angular distribution score, and every rigorous cross-audit of background noise contributes another essential piece to the sprawling puzzle of subatomic reality. The transition into the high-luminosity era will exponentially amplify this capability, transforming the scale at which experimental groups can interrogate nature. When particle beams resume circulation, detectors will face environments where roughly 200 proton-proton collisions occur simultaneously during every single bunch crossing. Managing that hyperdense thicket of overlapping tracks requires an entirely new generation of technological wizardry, from ultra-fast silicon pixel layers capable of sub-picosecond timing resolution to heavily shielded Faraday cages designed to protect sensitive control electronics from stray electromagnetic interference. These monumental engineering feats ensure that when the next wave of data arrives, it will possess a clarity and statistical power far exceeding anything available during previous runs. The intellectual gravity of this ongoing endeavor reaches far beyond the technical specifications of magnets, sensors, and computing grids, anchoring itself in the profound human desire to comprehend the fundamental order of the cosmos. Whether researchers are piecing together the family tree of doubly charmed baryons or keeping a cautious, vigilant eye on stubborn anomalies that hint at physics beyond the standard model, the underlying mission remains unchanged. It is an unyielding commitment to follow empirical evidence wherever it leads, submitting every cherished assumption to the harshest possible standard of proof. As the subterranean tunnels hum with the quiet intensity of maintenance work and global teams collaborate across continents to build tomorrow's technology, the stage is being set for the next great leap forward in humanity's endless quest to decode the universe. The transition into Long Shutdown 3 has fundamentally transformed the atmosphere across CERN's sprawling surface sites and subterranean caverns, shifting the primary focus from high-energy data collection to an intensive, multi-year engineering metamorphosis. With the final proton beams of Run 3 safely dumped from the 17-mile ring, engineers and physicists have wasted no time initiating the most ambitious overhaul in the laboratory's history. More than a kilometer of the original accelerator infrastructure is currently being systematically dismantled, clearing the path for the installation of cutting-edge high-luminosity hardware, advanced superconducting quadrupole magnets, and specialized crab cavities designed to tilt colliding beams with picosecond precision. While the physical collision halls lie temporarily dormant, the intellectual momentum within the global collaborations remains fiercely active. Thousands of researchers are dedicating their time to deep dive data mining, squeezing every possible drop of insight from the massive repositories accumulated over the past decade. The stubborn angular anomalies and rare B meson decay discrepancies that kept the physics community on edge are being reanalyzed under newly refined theoretical frameworks, while separate teams design next-generation tracking layers, such as all-silicon inner trackers boasting billions of readout channels, to prepare for the severe pileup environments of the coming decade. This quiet period between active beam runs serves as a crucial breathing space, allowing the international community to align its computational tools, upgrade trigger architectures, and steel itself for the technological leaps ahead. As infrastructure consolidation proceeds and specialized facilities like the North Area and Asaldi undergo extensive modernization, the global laboratory acts as a hive of collaborative purpose. When the accelerator complex gradually restarts its operations toward the end of the decade, it will inaugurate an unprecedented era of high-luminosity physics, bringing researchers closer than ever to resolving whether our deepest theoretical frameworks will hold or finally shatter. You are completely right, and I apologize for looping back on that update. Let's push straight forward into the next layer of the script without any repetitive looping. Beyond the physical overhaul of the 17-mile ring and the delicate sensor replacements happening inside the giant detector caverns, the impending high-luminosity era is driving a quiet revolution in how theoretical and experimental physicists handle information storage and distribution. The sheer scale of data expected to flood out of the upgraded collision halls is astronomical, dwarfing anything handled during previous runs. To prevent computing grids from collapsing under an ocean of petabytes, software architects are pioneering advanced real-time data compression protocols and hierarchical machine learning trigger architectures that run directly on specialized field-programmable gate arrays. These systems are designed to make split-second decisions on the microsecond timescale, intelligently isolating rare signatures like the elusive B meson decays, while permanently discarding uninformative background noise before it ever touches a hard drive. This computational leap is mirrored by exciting developments in auxiliary experiments scattered across CERN's broader surface campus, where smaller, highly specialized teams tackle fundamental questions that complement the massive general-purpose detectors. Facilities like the antiproton decelerator and the Isolde radioactive beam facility are running their own unique campaigns, probing the fundamental symmetries of nature by trapping antimatter atoms in magnetic bottles and measuring their gravitational free fall with exquisite precision. By dropping antihydrogen atoms and watching whether they fall upward or downward at the exact same rate as ordinary matter, these researchers are testing equivalence principles that form the bedrock of general relativity, searching for any subtle deviation that might link quantum mechanics to the gravitational pull of the cosmos. When all of these disparate threads, the high luminosity accelerator upgrades, the real-time machine learning triggers, the precision antimatter traps, and the rigorous global audits of flavor physics anomalies are woven together, they paint a picture of a laboratory operating at the absolute pinnacle of human capability. Every engineer tightening a cryogenic coupling, every data scientist optimizing a neural network trigger, and every theorist debating quantum chromodynamic corrections is playing a vital role in a grand multi-generational endeavor. As the multi-year shutdown steadily marches toward its eventual completion and the promise of a revitalized collider draws closer, the global physics community stands ready at the edge of tomorrow, anticipating the moment the machines in the dark finally fire back up to rewrite our understanding of reality.